Hello, everyone. This is Dr. Hurt, and we're going to be doing our fifth lecture today. It's on matter, so it's kind of getting us ready to talk a little bit about minerals. So today we're going to be talking about mostly kind of like some background chemistry, I guess, introduction to chemistry that maybe some of you have had, but some of you have not. So I wanted you to have some basic understanding of bonds and atoms and elements so that you can understand mineral bonds, which are, of course, the building blocks of the whole Earth. Okay, so I hope you remember that the Earth is, right, it's mostly made of rock, but it's about 1/3 metal. You guys hopefully all remember that the metal is in the core, and that metal is mostly iron and nickel. Okay. But it's mostly iron, right? It's about 90% iron. Now, the bonds between the minerals of rocks, those are very important. We're going to be studying those a little bit in this lecture. So anyway, I just start off with this first slide. It just kind of shows a very famous cave in Chihuahua, Mexico. If you didn't actually see this little man here, well, he's not a little man, he's a regular man. If you didn't see this guy here, you might just think this is a close-up of like a geode or something like that, but actually it's not at all. It's the crystals in here are really this big. These are gypsum crystals. Okay, gypsum is a very important mineral. Going to talk a little bit about gypsum in this class because it gets deposited in kind of desert environments of the past and has been preserved in the rock record. So you'll find gypsum preserved in the rocks even today. So what happened was that some very mineral-rich fluid must have flowed, right, been flowing through this cave at one time, back when the cave was perhaps a little bit lower, deeper in the ground, and it was under the groundwater level, and you had groundwater that was rich in gypsum, which is calcium sulfate, flowing through here, and it precipitated these crystals. Okay, just like if you were to take some salt water and leave it out and let the water evaporate off, you would get salt crystals. Okay, so these are kind of just that process, except much more, times 1,000. Okay, so rocks and metal are the building blocks of Earth, right? So Earth is made out of 2/3 rock, 1/3 metal, and the minerals are the building blocks of rocks. So we're going to study minerals next time. But what are those minerals made out of? Well, they're made out of atoms. Okay, so we're going to talk a lot about the atoms and bonds today. So minerals are the building blocks of rocks. All rocks are made of minerals. They're built up out of conglomerations of different minerals. Probably you know some minerals off the top of your head. Some famous ones are things like quartz. Okay, there's your quartz right here. Maybe some of you, when you were growing up and you're going through grade school, had little mineral kits. Maybe you had some mica in there, some fool's gold, right, which is pyrite, right? Those are all minerals. Fluorite is another popular one, so maybe you've seen those things before. So minerals are the building blocks of rocks, and rocks are made of minerals. Minerals in turn are made of atoms. Okay, so you'll notice this rock salt here. You may not realize that the salt you put on your food, it's a mineral, right? It's a mineral called halite. Okay, I'll spell that for you right there. Halite. Halite is composed of sodium and chlorine. And you notice that the sodium and the chlorine are in a very specific orderly arrangement. I talked about how the universe is an ordered place. It's a cosmos in the first lecture, and I don't think that's more clear anywhere else than in minerals. Okay, minerals are highly ordered, highly arranged in terms of their interior atomic structure. Okay, so here's the arrangement of carbon atoms in a diamond. You might not know that, or maybe you do, that diamonds are totally composed of carbon. There's nothing in a diamond besides carbon. Okay, it's just carbon. Which is exactly what coal and charcoal are made out of, right? So something as base as coal or charcoal, something as cheap and worthless as that, can be a diamond if the atoms are arranged in the right way. Here's actually a diagram of what mica looks like at the atomic scale. So these are all made out of atoms, and the way that the atoms are arranged is extremely important. You can't just have the right atoms, you have to have the atoms in the right order. Now, you might remember from the last lecture, he talked about Earth's structure and what the Earth is made out of, and there were some important elements that the Earth is made out of. In fact, of the 92 naturally occurring elements, the different kinds of atoms delineated in the periodic table. Here's your periodic table with all 92 naturally occurring elements, along with some that are synthetic and have only been composed, kind of man-made within cyclotrons and large-scale colliders. But the ones that are kind of in white are man-made elements, or ones that have gone extinct but maybe used to exist. So, for example, it might interest you to know that promethium used to exist, but it is all radioactively decayed. So we don't have promethium anymore. But earlier in Earth's history, there was promethium. So more than 99% of the rocks and minerals of Earth are composed of just 11 elements of the 92. So those are silicon, oxygen, iron, calcium, aluminum, magnesium, sodium, potassium, carbon, and hydrogen. So I'll circle them there for you. There's carbon, oxygen, silicon, aluminum. Over here on the left side, sodium, potassium, calcium, magnesium. Okay, and what else we're missing? I think, did I get them all? I think so, and hydrogen. Okay, so those are really the important. Oh, and of course, iron. Oh, don't want to forget iron. Iron's big, big, big. Okay, so those are the elements of Earth. Most of the Earth is made out of those elements. It might surprise you to know that 99% of the Earth is just made of those. Okay, so all that variation that we see in Earth is just kind of different jumbles of these 11 elements. Okay, so let's talk about how the atoms of the elemental periodic table are composed. Okay, so again, this is probably something you learned in grade school, even middle school, maybe not grade school, middle school, but it's important to know and understand because you have to understand how minerals bond together. So a atom is composed of a nucleus along with an electron cloud. Okay, so the nucleus is where all the mass is concentrated, and there are two subatomic particles there. That means particles that are smaller than atoms, subatomic particles. There's protons and neutrons. Now, a proton is a positively charged particle, carries a positive charge that is exactly the same in magnitude but opposite in direction as that of an electron. The electrons are small particles that occupy the space around an atom's nucleus in these very distinct clouds that are at different energy levels and different distances from the nucleus. Now, we don't really use that word orbit because they don't really orbit it. They simply occupy that space in a state of constant motion. The electrons, I mean. However, they do move, and they do move at very certain distances away on average from the nucleus. So these kinds of diagrams are correct in a certain sense, but you don't want to think of these things as moving like planets around a star. Okay, so E, when you see E here, that is the elementary positive charge, right? It's the charge of a single proton, and the charge of a single proton is about 1.6 times 10 to the 19 coulombs, in case you wanted to know. But you don't need to know that. You just need to know it's either negative or positive. Okay, so electron is negative, proton's positive. The mass of an electron is, you notice here, I put 0.0005 AMU, right? Mass of a proton is 1 AMU. So 1 AMU is defined basically as the mass of a proton, right? And all you have to realize here is that an electron is much smaller than a proton, much, much smaller. So it's only, 5/10,000ths the mass of a proton, so they're much smaller. Okay, so AMU is very small number. You don't have to know that. That's actually 10 to the negative 24 grams, not 10 to the 24 grams. Okay, so that's how that all works. Okay, now the number of protons here, when an atom is electrically stable, or I shouldn't say electrically stable, electrically neutral, the number of protons equals the number of electrons. Okay, so that the sum of protons and neutrons will just be be the same. So let's take a particular atom like carbon 6, or sorry, carbon 12. But getting myself all mixed up. So let's kind of work through this elemental symbol here. So this is the element name. That's the atomic number. The atomic number is the number of protons. Okay, it's the number of protons. Then okay, sorry for that. I'm back. I usually try to do these lectures before everybody wakes up in my house, so people are waking up and I was kind of getting distracted. But anyway, so where was I? So we have the elemental name, right? The atomic number, that's the number of protons, and that's the elemental symbol, C for carbon, right? And this is the atomic weight. We're going to talk a little bit more about atomic weight later. So, but it's basically the average weighted number of protons and neutrons within the element of carbon. And it's not a whole number because there are different what are called isotopes of the atoms that have different numbers of neutrons. So you don't need to understand that too much. So don't worry if that didn't quite make sense to you. So a proton has a positive charge in the center. You also have neutrons have a neutral. They have no charge. Okay, and they have the same mass, basically pretty close to a proton. And electrons have, of course, a negative charge. So there you go. A C atom has a nucleus with a charge of +6 and an atomic mass of 12. That's 6 protons, 6 neutrons. That's in the case of carbon 12. Okay. Now carbon 14 would have 6 protons, but it would have 8 neutrons. Okay. And 6 plus 8, you'll notice, equals 14. So this is the mass number. Okay, so the number of protons plus neutrons. Okay, I don't like this word orbiting here. I shouldn't have put this, but they're not orbiting electrons because they don't really orbit. They just are in a state of constant motion in a cloud around the nucleus. So the electrons have a total charge of -6 when it is electrically neutral. Okay, so electrons kind of, I don't know, I keep using this word orbit, but I don't like it too much. But they let's say, quote unquote, orbit in distinct shells. So there are very specific distances that the electrons occupy away from the nucleus. So in the first shell, in the first quote unquote shell, you have 2 electrons. Okay, there can only be 2 electrons in that first shell, that first energy level. In the second shell, you can have up to 8. Okay, now this is the thing about atoms, is that they always want to have their outermost shell full. So there are a very specific number of electrons that can occupy each shell. Okay, the first shell can only have 2 electrons. The next shell can only have 8 electrons, and subsequent shells typically have either 8 or 10. Okay, but for the purposes of this class, we're almost always going to be talking about shells that have 8. Okay, so atoms are always going to try to have their outermost shell full of electrons, and the reason for that is that they are most stable when they have that configuration, that specific electron configuration. Okay, so let's take a look at some different atoms and give you an example of this. So take a look at oxygen. Oxygen is element number 8. Okay, you'll see that's element number 8. That means when it's neutral, it's going to have 8 electrons and of course it's always going to have 8 protons. If it has a different number of protons, it'll have a different atomic number and it will be a different element. Okay, Now, we have, you can see 1, 2 electrons here, okay? So that means we need 6 more to get 8, right? So you get 1, 2, 3, 4, 5, 6. And you'll notice that we only have 6 out of the 8 electron possible electrons is 8 in that shell, but we only have 6. Okay, so that means that there are 2 spaces, right? So I'll write there 2 spaces. So this atom is not very happy. Okay, oxygen by itself is not very happy because it wants to fill up those 2. If that makes sense. So oxygen will actually usually combine with another oxygen and share its electrons in their outermost shell in a covalent bond in order to get that 8 rule. Okay. Now, chlorine, let's take a look at chlorine. Chlorine is element number 17. So we look at the first shell, there are 2. Second shell, there are 8. Okay, I'm not going to count them all, but there are 8. So that brings us to 10. In the third shell, we need 7, right? Because 7 plus 10 will equal 17. That's how many electrons we'll have when chlorine is electrically neutral. Okay, so that means we have 1 space here. Now let's look at argon. Okay, argon is a noble gas. Probably some of you know or have heard before that noble gases do not bond with other atoms. Okay, they kind of stay on their own. You'll notice it has 2 electrons in its innermost shell. It has 8 electrons in its second shell and has another 8 electrons, right? And that brings it to 18 total electrons. So it is happy. It doesn't bond with other atoms because it has totally full outer electron shells. Okay, so it's completely contented by itself the way it is. So that's why we call it a noble gas, is because it doesn't need to bond with anybody. So again, there's carbon, right? 6 electrons when it's electrically neutral, 6 protons. And when you're talking about carbon 12, right, which is 12 is the mass number, that's the number of protons plus neutrons, it has 6 neutrons as well. However, you can have a different number of neutrons if you have a different mass number, which there are. Like there are different forms of what are called different isotopes of carbon, like carbon 13 and carbon 14 that are radioactive. Well, not carbon 13. Carbon 14 is radioactive, but carbon 13 is not. It's stable. Carbon 13 has, for example, 7 neutrons. Carbon 14 has 8 neutrons. Okay. So let's talk a little bit about now kind of patterns we see in the periodic table regarding reactivity and how the periodic table is arranged. So the periodic table is arranged in a very special way. So you'll notice in the first row, okay, which is actually called the first period, there are 2 elements, right? There's hydrogen and there's helium. And the reason that there are 2 elements in the first period, the first row, is because it corresponds to those 2 electrons that are in the first shell. You'll notice in the next period there are 8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? That corresponds again to the 8 elements that are in the outermost shell. You'll notice the next one has 8, and the next one should have let's see, I think 10 plus 8, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, 10 plus 8, which is 18. Okay. So anyway, let's talk a little bit about these guys. Now these columns are called groups. Okay, so let's talk about group number 18. Okay, which is on the far right-hand side. Group number 18 are the noble gases. Okay, so we have helium, neon, argon, krypton. And you'll notice that for all these guys, this guy has 2 electrons. This guy has 2 and 8 in his outermost shell. And this guy has 2, 8, 8. So he's happy, right? All these, in fact, and if you do this with krypton, you'll notice krypton's happy too. So all of these atoms, in all these elements, in this row, or this group, are happy. They all are totally contented. They're noble gases, and they're unreactive. Remember that atoms only react and bond with each other and form minerals when they're unhappy. So you'll notice that if you look at all the different minerals and the different mineral formulas, minerals don't usually have any noble gases in them because the noble gases are not reactive. Okay, they only bond together when they're unhappy. So atoms with, in this group, you'll notice here, fluorine through chlorine, bromine. This is group number 17. Group number 17, they are eager to receive one more additional electron. So remember when we looked at chlorine, element number 17, it needed to have one more electron to be happy. Same thing with fluorine, right? So fluorine has 2 electrons in that first shell. Okay, so it has 2 electrons in the first shell. In the second shell, it's only going to have 7 out of 8, right? So it's greedy to have just one more electron. Okay, so all these are like that. All these atoms are like that. They want to have one more electron. These guys are very important because as oxygen is one of the most important elements in Earth, right? It is the most abundant element in Earth's crust. Okay, so oxygen is very, very, very important. Oxygen. Now let's take a look at. We already looked at oxygen, I think, right? Yeah. So we already saw it. We saw that it has 2 spaces. Okay, so it can take 2 more electrons. So oxygen, sulfur, selenium, all these are going to want to have 2 extra electrons to be happy in their little lives. Okay, so these are voracious. They're highly reactive, and they want to get those 2 extra electrons. Now, if you go to the left-hand side, you'll see that instead of needing electrons, let's take a look at these guys. Hydrogen is kind of interesting because hydrogen can be happy either giving an electron away or receiving one. So if you have hydrogen, here's hydrogen, has 1 electron only. It can either gain 1 and have 2 and be happy, or it could just lose all of its electrons altogether and be happy. So hydrogen's a little special like that. But let's take a look at sodium and potassium, because sodium and potassium, there's a lot of that in Earth's crust, right? So sodium is element number 11. So here we have sodium. It's going to have 2 electrons here. It's going to have 8, right? I'm not going to draw them all here. I'll just write 8 here. Okay, 2 here, that's 10. And in the third shell, it's going to have 1 extra. So plus 1 extra. So it's going to be desperate. Well, what do you think is easier? Is it easier to gain 7 electrons or just lose 1? So it's easier to just lose that one, right? So what's going to happen is this element is going to be eager to just lose that extra element, that extra atom, and shut it off. Okay, so when it does that, it's going to take on a charge. Okay, so if it loses, think about this. You have 11 plus charges in the center here. Now you started off with 11 negative charges in the electron clouds, but then you lost 1, so now you're down to 10. So the net charge on this sodium ion, once it loses its electron, is going to be plus 1, right? And after that, we say that it ionizes. Okay, so all of these atoms here, potassium, lithium, sodium, they're all going to, and hydrogen as well, they're all going to ionize and form plus 1 ions. Okay, they're going to lose an electron and form plus 1 ions. These guys are going to form, so magnesium and calcium, which are called alkaline earth elements, are going to lose 2 electrons, and they're going to have plus 2 charges. Okay, so what you're going to see is that these guys here, like oxygen, are going to have negative 2 charges. These are going to have negative 1 charges when they ionize. These are going to be, they're just not going to ionize. They're going to be 0. These are going to be plus 2, and these are going to be plus 1. Okay. So when these things ionize, that means they either lose or gain an electron, and they take on a net charge. That's the kind of charges they're going to assume. Okay. So sodium, right, is going to turn into sodium ion. That's what that sodium plus means, plus an electron. Okay, so that electron is going to disappear. It's going to go somewhere else. Okay, sodium ion plus chlorine ion will give us a mineral, our first mineral, which is NaCl, which is halite, right, rock salt. Okay, right. Chlorine is going to gain that electron, and it's going to become chlorine -1. Okay, For some reason with chemistry, instead of putting Na+1, we often just put Na plus, and we just forget the 1. Okay. So hopefully that all makes sense to you all. So this is a little story about how sodium and chlorine met and bonded together and fell in love. So this is just kind of funny, but it's just kind of a good way to think about this. So sodium atom is unhappy because he has one too many electrons in his electron shells, right? He wants to have a perfectly full outer shell, and he just has that one kind of extra electron that's tagging along. It's very annoying. So he's going to get rid of that, right? Now chlorine, on the other hand, is unhappy because she needs an extra electron, to complete her outer shell. And she's not going to be happy until she gets that extra one. So what's going to happen is that sodium's going to give up his electron. It's going to go flying in there into chlorine, and then they're going to stick together, right? They're going to want to be together because he wants to give away his electron and she wants to accept it. So now they're bonded together, and that's a very strong bond. Okay, so it's very hard to tear those two away from each other from now on. In fact, if you want to tear chlorine and sodium away from each other like salt, you want to make elemental sodium and elemental chlorine, you actually have to melt the salt down. You have to melt it down, which is very hot, so it melts at about 800 degrees Celsius. And then you have to run I think a pretty high voltage through it to break it apart. I think it has to be at least like 3 volts or something like that. I guess it's not that high, but I think it has to be something like that. So anyway, a little bit about cations, ions, anions. So when an atom loses an electron or gains an electron and it takes on a net charge, it's called an ion. Okay, that means that it's just an atom with a net charge. A cation simply has a positive charge. An anion simply has a negative charge. Okay, so there you go. Calcium plus 2, that is a positive charge. Potassium plus 1 is a positive charge. Those are cations. Anions, sulfide, 2 minus. Chloride, minus 1. Oxygen, O, 2 minus, right? That's going to be all anions. So, by the way, you're never going to have like calcium 3 plus or calcium plus 1, or you're never going to have potassium plus 3, okay? There's very specific numbers that they're going to assume for charges when they ionize, and it has to do with their electron configurations, as I explained before. Okay, so these are kind of the common charges that you're going to get on different atoms. Now, there are certain atoms, especially among what are called the transition metals, that they can have some variation in charges, but these guys on this side and on this side of the periodic table are going to always have the same charge. Okay, so carbon is plus 4, silicon is plus 4, sodium is plus 1, magnesium plus 2, potassium plus 1, calcium plus 2. Iron here can be 2 or 3. Okay, and then oxide is always negative 2. Sulfide it can actually be a couple different things. It can be negative 1 or 2. Okay, negative 2. You could also fluoride and chloride, both negative 1s. Okay, so there's some common charges on some of the things, common elements that are around, right? So you can see that the most common elements that we have in the Earth are all represented here: silicon, oxygen, iron, magnesium, calcium, sodium, potassium, and oxygen. Okay. Now, ions are going to bond together. Oh, excuse me. Oh, I had to sneeze right in the middle of the lecture. Sorry. Ions will bond together to make electrically neutral, net charge of 0 compounds during an ionic bond. So ionic bonds are when two ions combine together in order to form an electrically neutral compound. Okay, electrically neutral compound. That means it does not have a net charge. Okay, so remember we talked about one very famous ionic compound, ionic bond between sodium and chlorine. Okay, sodium is a +1, chlorine is a -1. If you combine their charges together, there's one sodium, one chlorine. You combine it together, it's 0, right? That's electrically neutral. So it's an electrically neutral compound now, and that's an ionic bond. Okay, so bonds between ions, that's an ionic bond. Okay, and let's talk a little bit about some examples. Okay, so magnesium is a 2+ plus oxygen, a 2-, is going to give us MgO, right, which is a mineral called periclase. There's a gem of periclase. Okay, so magnesium and 1 oxygen. Okay, now it's not going to be magnesium 2 oxygen, because there's only that would not be electrically neutral, right? So because then you would have 4. You would have a positive charge of 4, because you'd have 2 + 2 magnesiums, and you'd only have 1 oxygen at 2-, and so it would have an electrical net charge. So we don't want that, right? So that's why these formulas have to be very exact. It's a very precise number of each element to the others, very precise proportion. It's not going to change. Okay, silicon, 4+ plus 2 oxygens at 2-, that's going to be electrically neutral, right? 4 plus 2 times -2 is going to be 0, and that's going to form a mineral, SiO2, which is quartz. Okay. Now you can also have 2 magnesiums, 2+. Okay, so that's 4 plus. Then you have a silicon, 1 silicon, 4+. That's another +4. And then you can have 4 oxygens at 2-, so that's -8. It's electrically neutral, right? 4 plus 4 minus 8, and that gives you a mineral olivine. Okay, so if you add up all the charges on the left side of the above equations, you notice they always come out to 0. That's because they are ionic compounds. They're ionic bonds, and that's how that mineral has formed. Okay, now ionic bonding isn't the only kind of bonding. There are other types of bonds called covalent bonds that involve, instead of kind of giving one electron up and taking another electron, it involves the sharing of electrons. So, for example, CO2, that's actually a covalent bond. And what the carbon does is it shares its electrons with the other oxygens. And if you count up the electrons now in each of these electron clouds, you'll notice it ends up being 8. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right, and the same on this side. So you'll notice that everyone has their 8 electrons that they want. They're happy in their outer shells, and they've just done it by sharing electrons rather than one giving to the other. Okay. So another example of a covalent compound is something like H2O. Okay, H2O shares the oxygens and hydrogens share their electrons with each other, and this, by the way, creates a very unique geometry to the molecule. You'll notice that that's the geometry of a carbon dioxide molecule, right? It's a straight line. It's kind of interesting, right? So you have an oxygen, right, a carbon, and an oxygen. It's in a straight line. H2O is not like that. Water's not like that. Okay, so water ends up having hydrogens kind of on one side and the oxygen on the other. And actually what happens is that ends up creating what's called a dipole. So it ends up that you have an electrically negative side here, an electrically positive side here. And that is, by the way, why water is such a powerful erosive agent, and why it can dissolve different minerals and things like that and break down. I mean, you all know how powerful water is, right? You leave a car out made of solid steel. You leave out a car in the rain for a few years, you know what happens. It breaks down pretty quickly. So that is, by the way, why water is such a powerful erosive agent, powerful chemical agent. Okay, so it's got that what's called a polarity to its molecular structure. Okay, negative side and a positive side. Now, I want to also talk about these little bonds that are a little bit strange called van der Waals bonds or van der Waals forces. I do ask a little question about that. You don't need to understand these in great depth at all. In fact, they're very, very difficult to understand. You have to know quite a bit about chemistry and quantum, even quantum mechanics, to start to understand them. But just know that they are very weak, and they're very common in minerals, but they're very weak bonds that are only strong at very close distances. Okay, so once any distance between the two atoms, once it expands and stretches out, it's going to lose the strength of that bond. So some very common examples of van der Waals bonds are between, or actually in graphite, like in your pencil lead. So you might not realize that your pencil lead is a mineral. It's a mineral called graphite, and it's pure carbon. Okay, just like diamond. So isn't that interesting that the elemental formula of diamond and graphite are exactly the same? And what's kind of cool is that graphite is the weakest, it's the softest mineral, and diamond is the hardest mineral. Yet they're made of the same thing. So it's pretty neat that, I don't know, it's like, it was very symbolic that nature has done this, where you have the weakest mineral and the hardest mineral made of the same things, but the atoms are just arranged differently. So when you have so this, by the way, an answer to one of your questions. It's like it's on one of the last questions. So when you have minerals that are the same chemical composition, but they're different structures, they're different minerals, those are called polymorphs. Okay, poly means many, morphs means form. So these are kind of many forms. Okay, so you can see that even though the composition is the same, it's carbon, the form of the arrangement of the atoms is different. Okay, so this is weak, this is strong. These van der Waals forces, so you have, what do you have? You have these sheets of carbon atoms. You can see these different sheets of carbon atoms. And keeping these sheets together are these van der Waals forces that are relatively weak. And so what happens is when you write with your pencil is you're actually slaking off these sheets. So these sheets, you're breaking the van der Waals forces and you're slaking off the sheets. Okay. So diamond has all covalent bonds between the different atoms. In fact, by the way, you can only have covalent bonds between atoms of the same element. You can't have ionic bonds. So the sheets of graphite are kept together by covalent bonds, but the sheets themselves are attached together by van der Waals forces. Okay, so ionic and covalent bonds are very strong. Van der Waals forces, which are molecular type bonds, are relatively weak. Okay, ionic compounds often dissolve in water too. That's another important part of ionic bonding. Okay, but covalent bonds, I don't know, actually, I kind of feel like maybe I shouldn't put it, they're the strongest. They can be very strong, but ionic bonds can be very strong as well too. So, but the strongest kind of bonds are when you form these networks among the different atoms, right? So you can see almost the kind of like architectural design almost that's manifested in the diamond atomic structure. So it's kind of cool. Kind of reminds you almost like of a bridge or a building, and it's the reason that it's so strong. So just kind of key points today. So I'm all done with the lecture now. About bonding, right? We have ionic and covalent bonds. These are kept together by electrostatic attraction in ionic bonds, right? You have different ions that are attracted to each other because they're positive and negative charges. That's called electrostatic attraction. Covalent bonds are held together by electron sharing. Okay, and those kinds of bonding determines a lot of the physical characteristics, how hard the mineral is going to be, whether it dissolves in water, whether it's going to be soft or whatever. Everything's determined by these bonding characteristics. So anions are negatively charged ions. Cations are positively charged ions. Ions themselves are just atoms with a net charge. Okay, so either positive or minus. Minerals are most often just ionically bonded together, and they're just combinations of cations and anions. And really, you could go there. Remember when I gave you that sheet that showed you, that slide that showed you the different common bonds different common charges on the different ions, you could go there and make your own minerals and just combine minerals in a way as long as they're electrically neutral. And I would bet you that probably there is really a mineral with that formula that you make. So anyway, that's all I'm just gonna end right there. So next time we're going to talk more in depth about minerals. But for now, this is all, and hope you have a good week. And make sure hopefully you got everything that's on your lecture assignment, and let me know if you need any help whatsoever in the class. I'm here to help you. So I'm going to sign off here now. Have a good week.